Okay, let's get going. Finally, full screen. Okay, so today, we're going to start talking about linear regression models. We're going to use the rstanarm R package, and we're going to finally start really updating from updating prior beliefs into posterior beliefs by conditioning on data and drawing from the posterior distribution using STAN. So as usual, I'm a Columbia employee. Columbia developed STAN, seeking additional grants, using STAN for business purposes, and that creates the appearance of a conflict of interest, in part because a number of companies are, using rstanarm, using rstan to do related things. So one thing that I wanted to talk about last time, and the technical details were not cooperating, I will try to do this time to illustrate how MCMC Flow works. So if you define a function that returns the negative of the logarithm of the posterior kernel, or the kernel of the distribution that you are trying to draw from. In this case, we're just trying to draw from a bivariate normal distribution. So we could do this analytically, but I want to try to show how this looks with a plot. So how do I make this bigger? Zoom. Okay, that helps a bit. It's just compiling for 1 second. Hopefully 1 second. The computer seems really slow for some reason. Anyway, we define a function called, in this case, dBVN, which turns the negative of the logarithm of the binomial PDF, and then we can create a, forgot to do the first part of this, which was my STAN function. So we define a function that returns the negative of the logarithm of the PDF of the bivariate normal distribution. That's dBVN. We're going to make a plot, x on one axis, y on another axis, and the z-axis is going to have this negative of the logarithm of the posterior kernel. And then we want to show how does a point which represents the position of x and y move under the physics analogy that we were talking about last week. All right, third time's the charm. Come on. Come on. Y'all see a plot?
You also sent us an email.
Yeah. Not sure everybody read that. Come on. Come on, plot. Come on, plot. Where's the damn plot? They're rerouting my plot over extraordinarily slow internet connection from 3 buildings over. Come on. Come on. Plot. All right, we may have to come back to the plot. So one thing that we can learn really quickly while the plot is happening, we need to learn a new distribution for the rest of some of the things that we're going to use later today. That is the so-called gamma distribution. Gamma distribution is going to be defined over a sample space that includes all non-negative numbers. It has the PDF here whose kernel involves x raised to the power a minus 1 multiplied by e times negative bx. This is going to depend on two positive hyperparameters, a and b. A is known as the shape parameter, b is known as the rate parameter, and aside from them being positive, those two are fairly difficult to interpret, so we can utilize any of the other characteristics of the gamma distribution, and if we select any two of these, we can invert to obtain values of a and b that are consistent with our beliefs about how about x. So the first and probably the easiest one to deal with is the mode, which if a is greater than 1 is defined as a minus 1 over b. Otherwise, the gamma PDF is going to go to infinity as x gets closer to 0. So that is fairly easy to deal with as long as a is greater than 1. Regardless of whether a is greater than 1, the expectation of a gamma random variable is a over b. So the expectation is always going to be greater than the mode. If the expectation exists, we have a pretty good expression for expressing the median. This also requires a to be greater than 1. But anyway, the median is pretty much a linear function of the expectation. So that's going to be between the mode and the expectation. Also, the variance is equal to a divided by b squared. So if you pick any two of those, you ought to be able to solve for a and b that is consistent with what you believe about x. So the gamma distribution is a very flexible one. Includes a couple of special cases that we've already mentioned. One, if the shape parameter a is equal to 1, then it simplifies to an exponential distribution with rate parameter b, and the rate is equal to 1 over the expectation of an exponential random variable. And if a is equal to b over 2 and b is equal to a 1/2, then the gamma distribution specializes to the chi-squared distribution with v degrees of freedom, although v need not be an integer. So that is a pretty useful distribution that you will encounter from time to time. We can plot the PDF and the CDF of the gamma distribution here with a shape of 2 and a rate of 1. You will also see the gamma distribution parameterized in terms of a shape parameter and a scale parameter. That, honestly, I find more useful, but it's not the way most software does it. In any event, the shape is equal to 1 over the rate. So if the rate is 1, that's equivalent to saying that the shape is 1. So here we have a plot. In the black line, we have CDFs. It rises fairly quickly, then flattens out. Obviously, x goes to infinity, but the change in the CDF, which is represented by the PDF, becomes essentially 0 pretty quickly, at least for these two values of the parameters. And in the red line, we have the PDF, which is just the partial derivative of the CDF with respect to x. So you see, initially it has, you know, a pretty steep slope, then an inflection point, and then the slope goes to about 0 as the CDF flattens out. And so you can shift this over by making a larger shape parameter, etc. But this is a pretty good distribution for things like variances, standard deviations, etc., that are constrained to be positive. Questions about the gamma distribution? All right, where's my plot? Still no plot? Yeah. All right, we'll have to learn something else. Okay, so first, as we get into regression models, we want to talk first, chronologically at least, as to how to think about ordinary least squares, which is one estimator, a frequentist estimator of a linear model. So always remember, there are multiple estimators of the same model, or multiple estimators of the parameters of a model with a linear data generating process. In fact, there's more than one frequentist estimator of a linear model, without even beginning to mention the Bayesian estimators of a linear model. Of course, with the Bayesian approach, there's sort of only one estimator really, which is to use MCMC, presuming that you can't do it analytically. But there's as many different models as there are ways to specify priors on the parameters that go into a model that is linear in the parameters in the likelihood function. So we want to talk briefly about what is assumed and by the ordinary least squares estimator of a linear model. So if we write a function to draw from the sampling distribution of the OLS estimator, the distribution of the parameter estimates across different realizations of the outcome variable, it would look like this. So we want to set up a matrix that is S by 3. S is the number of simulations that we want to do. We have 3 columns, one for the estimated intercept, one for the estimated slope, one for the estimated variance of the errors. We're going to do this all conditional on a single predictor, X. So the number of rows in X is N, the number of observations that we're dealing with. We want to subtract 2 because we're going to have to divide by N minus 2 later on in our loop. Next thing that we do, oh, I suppose I have my laser pointer here, is set up another vector also of length N, which I call X underscore, which is just X in terms of deviations from its mean. So centering the X variable. This is a trick that both frequentists and Bayesians use in order to make the derivation of what they're talking about simpler. Basically, if you center your predictors, then the intercept can be thought of as the expectation of the outcome for someone who has mean levels of the predictors rather than someone who has 0 in the predictors, which might not even be a reasonable value. All right. Then we define the sum of squares of the centered version of X, store that as a constant in a real number. And finally, we create, or almost finally, we create another vector of length N, which is going to be the conditional expectation of Y for a given X and given values of alpha and beta. Again, we're doing this from a frequentist perspective. So alpha, beta, and sigma, which is the standard deviation of the errors, just are passed in to this function ostensibly by nature. But one of the things that frequentists have been able to prove is that the properties that we're going to see here hold for any legal value of the parameters, which just basically means sigma has to be positive. Anyway, we create mu, alpha plus beta times X centered to be the conditional expectation of Y, and then we'll allocate but not fill in yet a vector of length N for our outcomes. Then we're going to loop over the number of simulations that we want to do. Inside our loop, we're going to loop from 1 to the number of observations, each time creating a Y variable that's equal to the corresponding value of mu plus a draw from a normal distribution with mean 0 and standard deviation sigma, this representing the error that we're thinking of being drawn every time we loop through one of these simulations. So we create our outcome variable Y that way, and now we're ready to estimate the parameters. If we do this with the centered version of X, then the intercept is simply equal to the sample standard deviation of Y. We stuff that into the first column. Second column holds our estimated coefficient, which is going to be sum of the vector element-wise product between Y and X centered, divided by the sum of squared values of X. That's just the formula for the OLS coefficient in the bivariate regression case. And in the third column of X, out, we're going to stick the estimated variance of the errors. So that's Y minus the intercept minus the slope times the predictor. That creates a vector of residuals. We're going to square those. We're going to sum those up. And we're going to divide by n minus 2 in order to get the estimated variance of the error term. Rashika. So this is not Bayesian. Right. So this is not a prior on mu. This is a deterministic construct if you take alpha, beta, and x-centered as given. There's no distribution here. It's just algebra. Right. And so this is going to be fixed rather than something that frequentists have a prior over because they don't have a prior over anything. Anyway, we get estimated intercept, estimated slope, estimated variance, do that a bunch of times, return the thing at the end, and this gives us a sense of what the distribution of the OLS estimator is in this case. Robert.
Okay, so we're, before this function, we've done OLS, we've gotten out estimates, and we're putting them in to get the same distribution. Those estimates now. Okay,
no.
So what are alpha and beta? What are they?
Those are the true population parameters.
Oh.
Right. So we don't, you can think of it this way. We don't have our outcome variable yet. So before we see the outcome, what is the probability distribution of the OLS estimator across data sets that we could collect?
Okay, so when we make that vector mu, we're constructing the outcome from the parameters we set back.
Yes, the parameters we pass in. The true population parameters.
And that's why there's no error on that one.
Right. So mu is fixed. It doesn't have any noise in it. But when we create a realization of y, it's its conditional expectation plus a realization of the error distribution. Right? So we get all this, and this tells us a probability distribution for the OLS estimator across realizations of y. And so we expose that, we run it like 100,000 times, we take the average down the columns of the matrix that gets returned, and you can see that this is not bad by frequentist standards. This OLS estimator is unbiased. We gave it a value alpha equal 1, beta equal 2, sigma equal 3. We got back 1, 2, and 9, but the third column here is a variance rather than a standard deviation. So this should be 3 squared or 9. And so the OLS estimator is an unbiased estimator across realizations of y. So across data sets with y in it. Now, you might have noticed something weird or even weirder than the typical frequentist way of doing it. This is evaluation of the OLS estimator across data sets where x is the same, but y is different. Now, how it is that would work in a social science context, I don't know. I mean, usually it's hard to imagine these things being even done more than once, but if you could, like you take a survey of people or whatever, you would expect in different data sets, x would be different in addition to the outcome variable y. Now, you can do this without the assumption that x is fixed. However, you can only get results as n goes to infinity. OLS is one of the few estimators for fixed x. You can actually show it's unbiased regardless of what n is, even if this idea of repeated data sets with x always being the same and y being different makes no sense in a social science context. However, it made a little bit of sense back in like the 1800s or early 1900s, when the way in which they were thinking about applying this was not to people or surveys. They didn't really have surveys, but applying it to a situation like how big do plants grow? And in that situation, you could sort of imagine like a greenhouse, and the greenhouse master or whatever chooses the temperature and the humidity and the amount of water that's given to the plants and sets that to the same thing across realizations of different seeds that get put into pots and stuff. And then you see how tall they grow, and then you do a regression of like plant height on temperature or something like that. So in that context, you can kind of imagine x being fixed by the researcher and the outcome randomly differing from plant to plant. In the context of people, it literally makes no sense. But given all that, you can derive the estimator of OLS, and it is unbiased for the parameters across realizations of the data set with different values of y. So if we go to make plots of the test statistic, so we'll make sum of squared x again. We'll create the true standard error, which is equal to the square root of the error variance, which is 9, divided by the sum of squared x. Then we can plot the CDF of our estimated slopes minus the true slope, which is 2 in this case, divided by the true standard error, which is 9 over whatever SSX is, all square rooted. And we get the plot with the black line for the CDF of this particular ratio. If we overlay a standard normal CDF and put it in red dashed lines, you can see it exactly lines up with the black line that we showed before. And so you actually don't need to do a simulation. You can show this with math, but I think it's probably less intuitive than showing it with simulations, that the distribution of this ratio across data sets with the same x follows a standard normal distribution. So if you knew the true slope, which is 2, if you knew the true standard error, which is this thing here, you could construct this distribution and it would be a standard normal PDF. And so you can go, you know, over here, like 0.975 or whatever, over to the curve, down to some value. It's going to be like 1.96. And that would be the value such that 2.5% is to the right, and then there's going to be 2.5% that's less than negative 1.96, etc. Salif.
I'm not entirely sure if I understand x. So x is just like an independent variable, it's 1?
Yes, you can be whatever you want. Here I drew it from the exponential distribution, but point is it remains fixed across repeated applications of the OLS estimator.
But I'm just thinking about like if it's an actual variable and especially if it's a discrete variable, then of course like the values are, I mean if it's like income 5 categories, it's like across different data sets you have these 5 categories. It's just like different subjects.
No. It has to be the same values. So if you do a survey and you ask people what their income is and you give them 5 things, of the 1,000 people, you need exactly 400 poor people, 100 middle, etc. And that has to be the same across data sets. And there's no way you could ever do that by chance if you were doing a survey or really anything involving people in a social science context. But if you were to somehow do that, then you could figure out the distribution of the OLS estimator across realizations of y, which have error in it. And the realization of that estimator, if you subtract the true value, divide by the true standard error, is going to follow a standard normal distribution. And there's all kinds of things we know about a standard normal distribution. However, 2 things that we don't know ordinarily are what is the true value of the slope and what is the true value of the standard error. Because those are the things that we're trying to estimate. So if we use estimated standard error, in which instead of using the true value 9, we use the values that we got in the 3rd column when we did all these simulations, take the square root of that, still subtract the true value of the slope, which we somehow know, of course, but divide by the estimated standard error, which is actually somewhat reasonable. I mean, we can estimate that. Then we do the plots. Looks not quite the same as it did before, and that's because we're dividing by an estimate rather than dividing by the true standard error. But the distribution of this is known. It is the CDF of a T distribution or student T distribution that has n-2 degrees of freedom. In this case, I gave myself 17 observations. So there are 15 degrees of freedom. And then when I overlay the red line for the CDF of the student T distribution over the black line, which is the CDF I got from my simulations when I do this ratio, again, they exactly line up on top of each other. So you don't need to do the simulations per se. It can be proven that if you divide by the estimated standard error rather than the true standard error, the distribution of this is student T rather than standard normal. But of course, the student T distribution approaches the standard normal distribution as the degrees of freedom approaches infinity. And really, even if it's more than like 20 or so degrees of freedom, you can't really perceive the difference between a standard normal distribution and a student T distribution. So you might say, and it would be quite reasonable to say, that this still is not useful for science, because in addition to all this sort of weirdness in this with X being fixed across data sets, not knowing the true values of the parameters, etc., you would need to know at a minimum the true value of the slope in order to construct this ratio, even if you could divide by an estimated standard error. And so at this point, frequentism, at least after 1940 or so, takes a turn for the bizarre. It says, okay, assume a value of beta for the population. And if you assume the value is 2, then the distribution of this ratio thing is going to follow a standard normal, or student T, basically standard normal, but not quite, student T distribution with n-2 degrees of freedom, because you estimated 2 parameters, the intercept and the slope. Okay, so we got, all right, so what do you assume for a value? Well, if you assume it's 2, then you can derive this thing. And so the sort of dance that people applying frequentist estimators do after estimating the thing is assume a null value for the thing that you're estimating, calculate for the one realization out of the 100,000 that you get here, what is the value of this T ratio, which is your estimate minus your assumed null value divided by your estimated standard error. So assume it's some value. And if you assume it is the correct value, then we know what the distribution of the test statistic is. And so you can calculate whatever realization of the test statistic you might get for your particular data set. Let's say it's some number around 5. You go up to the curve that's applied by your assumptions, and you see the probability of observing a T ratio that is more extreme than 5 is very small. There's not a whole lot of probability left here. If your null hypothesized value that you assumed when doing this was correct. And so it's basically assume a value of the slope for your null hypothesis. Check what is the probability of getting something more extreme, conditional on that null hypothesis being true. If that probability is sufficiently low, by convention less than 0.05, then unassume whatever value you plugged in for your null hypothesis in the first place. So assume something, evaluate the implications of that, given that your assumption is true. If you find out the probability that somebody else would get something more extreme than you, conditional on the null hypothesis, if that probability is sufficiently low, then give yourself a do-over on the assumption and publish it. Because that's what we're doing here. So that seems like a very weird way to do scientific inference, and it is, but it all stems from setting up the probability to be functions of the data conditional on the parameters, which you don't really know. You're trying to estimate. But if you set up your probability of functions of the data given the parameters, then all you can really do is make an assumption about the parameter and see if your data is, grossly extreme under those assumptions. And if it's sufficiently extreme under those assumptions, then don't assume your null hypothesis is true anymore, leaving open the question of what you should assume after that. Frequentism doesn't really say. And so that's sort of an unsatisfactory answer, but that's what you're left with after spending all these years on a research project. Yes, Sebastian.
This is sort of like, we're not often, this is something we'll talk about, we're not often social science, we're not really doing pure hypothesis testing. It's like, is there an effect or zero effect? Like we actually want to estimate.
Right.
Like that's the big distinction of what we're talking about.
That is an important point to keep in mind. However, historically and currently, journals typically are going to report tests of a null hypothesis that some coefficient is zero, exactly zero. Irrespective of the fact that's not super important from a scientific perspective, and what everyone means is not assuming that the coefficient is exactly zero, but something more like assuming the coefficient is so close to zero that it's not important. But you can't really test a null hypothesis that a coefficient is not important. That's like too vague. We can only derive the distributions of these things under precise assumptions, such as this coefficient is exactly zero. And in a lot of social scientific contexts, it's extreme. It is extreme, but also extremely silly to assume a coefficient is going to be exactly zero and then, work out all the implications of that. But suppose we were to make the null hypothesis that the coefficient in the population is zero, test against a one-sided alternative hypothesis that beta is positive, do all that. Instead of subtracting 2, which is the true value, subtract 0, which is the hypothesized true value. Do this thing. What proportion of the time are the realizations of this greater than the threshold, which is the 90% value under the T distribution with 15 degrees of freedom? We come up with a number like 0.8, which is the power of the test. So if you design or pre-register something, a study, say I'm going to get 17 observations, estimate an intercept or a slope, I'm going to test the null hypothesis that the slope is 0 for these realizations of X. Before you look at what Y is, there's an 80% probability you'll be able to reject the null hypothesis that the coefficient is 0 in favor of the alternative hypothesis that the coefficient is positive. So in 80% of the data sets, that will happen. Not 100. So 20% of the time, you would fail to reject the null hypothesis that the coefficient is 0, even though in this data generating process, we constructed it with a coefficient of 2. This is because this is a pretty small sample, and so sometimes it's unable to detect what might be a rather large coefficient in the population. But let's say, best case scenario, you reject the null hypothesis that it's 0 in favor of the alternative hypothesis that it's positive. At best, even if you sort of ignore all the weirdness of this, you're left with the conclusion beta in the population is positive, or that's my conclusion. You can't really make probabilistic statements like beta is probably positive because beta is not a random variable and it doesn't have probability distributions associated with it. But you can sort of say, okay, I reject the null hypothesis, it's 0 in favor of the alternative hypothesis that it's positive. So I'm going to move forward under the conclusion that beta is positive. even if you ignore all the weirdness that led you up to that situation, knowing that beta is positive is insufficient to make a decision or some sort of real scientific progress or something like that. It's not enough to know what the sign of beta is. You need to know how big it is or have some estimates, distribution for how big it is in order to evaluate the costs and benefits under uncertainty. And so if this was like, you know, something relating the incidence of lung cancer symptoms, and X is the amount that you smoke, saying that, okay, the incidence of lung cancer symptoms, the coefficient with respect to how much you smoke is positive, doesn't really tell you how seriously sick you're going to be, how, if you get lung cancer, how much it's going to cost you to get treatment for this, how much your life expectancy is going to get shorter as a result. All we know is it's like not going in the good direction if we come to the conclusion that the coefficient is positive. Now, you can say, okay, well, I don't just find that it's positive, OLS gives me a particular number, like 1.46 or something like that. But there's no real rigorous justification for you believing it's 1.46. Really, all that the frequentist thing is being able to get you is 80% of the time in this situation to reject that it's zero in favor of alternative that it's positive. You don't really get exactly uncertainty as to not just is it a positive number, but how big, how small.
Hypothetical, but what if, like, should we consider the case where people assume that beta equals zero? What if they keep on incrementing, like beta equals 0.01? Like, can't they, like,
Yes.
the number?
So this whole thing assumes not only that X is fixed and the population parameters are fixed, but the null hypothesis is fixed. And so if you were to conduct multiple tests with multiple different null hypotheses, the distribution of the test statistics would not follow this known t-distribution. And if you were to use the t-distribution to calculate your p-values or to decide your rejection and whatnot, you would end up doing the wrong thing. So rejecting it not 10% of the time, even when the null hypothesis that the coefficient is zero is true. Now, all that said, when people do applied research with frequentist methods in practice, there's all kinds of things that are assumed by the theory to be fixed that are not actually fixed. So it's extremely common, bordering on ubiquitous, that, okay, you apply OLS once, you get an estimate that, you know, isn't statistically significant, or it has the wrong sign, or it's, you know, doesn't really seem big enough, and you're like, well, that doesn't seem right. I need to change my model. Maybe I need to exclude a couple of outliers, and I'll re-estimate it again. Now, doing so completely screws up the assumed distribution of, you know, if we do this over and over again, but do exactly the same thing every time, then we can figure out the distribution of the test statistic. But if there's some like choose your own adventure social science thing where if it turns out to be negative, then you're going to estimate some other model, and if it turns out to be positive, then you stop. Like, that's going to be a completely different distribution of the test statistics that's probably going to be impossible to work out analytically. And so it's not as if people who use frequentist methods don't have beliefs about what the parameters are, but instead of expressing those beliefs in prior distributions explicitly and upfront, they sort of keep them in reserve. They estimate OLS, or maximum likelihood. And if they get estimates that are sort of not too consistent with what they believed the parameters would be going into the process, then they just change the data, change the model, change the estimator, change the random number seed, something, until you get something that you do believe. So all the stuff that Fisher was talking about, railing against introducing beliefs into the process, is really not something that is achieved by people using methods that pretty directly trace themselves back to Fisher. Questions about power of a test? Again, this is power over a test across many realizations of the y vector, keeping the x vector fixed. So it's power for sort of impossible scenario to begin with. Salif?
That's not completely different. I don't want to get off topic, but so for randomization terms, is that like different? Or is it
Yes. So that really is conditional on your experiment. And in that context, p-values make a little bit more sense. However, you're still at the end of the thing left with a conclusion. At best, average treatment effect is not 0. I can maybe reject it in favor of alternative. The average treatment effect is positive. But if you're like a drug company, knowing that your drug helps is insufficient for the FDA to decide whether to approve it. We have to evaluate the costs, and we have to know how effective it is, not just that it's like better than nothing. All these sorts of things. So really, like, this doesn't get you far enough to really be doing anything that useful. So another thing that is not so useful is a posterior distribution that we can make line up with the distribution of the OLS estimator across data sets here. And in order to do that, we have to assume priors, which are improper. So merely that alpha and beta are any real numbers. And we have a Jeffreys prior on the precision tau, where again, tau is defined as the reciprocal of sigma squared, the variance of the errors. Again, just as with OLS, assuming that the errors are drawn from a normal distribution with standard deviation sigma. So if we take this prior right here, multiply it by a normal likelihood, this, so accumulated overall in observations, y minus alpha minus beta times x, that's the residual squared, e, all this. You can simplify this to this expression, tau raised to the power n minus 2 over 2, e raised to the power negative tau over 2 times the sum of squared residuals, sum of squared errors. So we can simplify it down like that. Now, a useful trick, although how it is you apply it in any particular situation varies. But here we have, okay, a posterior PDF, or at least a posterior kernel for alpha, beta, and tau, which are the 3 parameters we don't know. We can use the multiplication rule to write this as the PDF for alpha and beta given tau and the data, multiplied by a PDF for tau given the data alone. So multiplication rule implies the thing on the left. It turns out this is one of the few 2-dimensional integrals we can actually do analytically. So we can take the whole posterior kernel, integrate alpha and beta out of it, and we get an expression here, tau raised to the power n minus 2 over 2 minus 1, e negative tau n minus 2, and the OLS estimate of the error variance, all divided by 2. And if you look at this, you can recognize it as the kernel of the gamma PDF that we just got through talking about, with shape n minus 2 over 2 and rate n minus 2 times sigma square hat divided by 2. So you can actually write the posterior distribution of tau in terms of the OLS estimated error variance, like this. So this implies the posterior PDF for tau is a gamma distribution. It has a name. We have that. Okay. So then what is the distribution of alpha and beta given tau and the data? That one is actually simpler, but I don't want to really dwell on it. They both come out to be, oh, this is messed up, normal and the expectation of the normal distribution for alpha is y bar. The expectation of the beta distribution is beta hat from OLS. And the standard errors of those two that go into the normal distribution are the same as the true standard errors that you get for OLS, namely sigma divided by the square root of n minus 2 is your standard error for the intercept, and sigma divided by the square root of n minus 2 multiplied by the sum of squared values of x. That's the standard error for the normal distribution for beta. So what is the main point of all this? There are priors, albeit improper ones, albeit ones that no one would voluntarily choose, such that the posterior distribution of the parameters, given the one data set that we have, is the same as the estimated sampling distribution of ordinary least squares. So conditionally normal for alpha and beta given tau, and then we integrate over tau, they end up being t distributions. So even though this posterior distribution is conditionally normal, and the distribution of the OLS estimates are conditionally normal, and they are the same conditional normal distribution, so they have the same expectation and they have the same standard error. The posterior distribution is still a different concept than the distribution of the OLS estimator. Posterior distribution is what you should believe if you had these priors and you see these data about the parameters. Sampling distribution of OLS is something objective, the distribution that would hold if you could do this over and over and over again, albeit with the same x and a different y. But anyway, they are the same distributions, but they're not the same concept. So what this really implied in the days before MCMC is that Bayesians could use OLS estimates and figure out one posterior distribution of interest analytically, or one more posterior distribution of interest analytically, rather than doing MCMC, which was important in the days before MCMC was invented, or at least known in the social sciences. So back in the 1940s or whatever, Bayesians could get this posterior distribution, but they had to accept the fact that we had improper priors on the alpha and beta, and kind of a weird Jeffreys prior on tau. We talked about how Jeffreys prior on sigma might make some sense because sigma is a scale parameter, but Jeffreys prior on a precision really doesn't. All it does is allow us to derive this posterior distribution analytically in closed form. What people take it to be is that, well, we don't really have to do Bayesian stuff. We can just do OLS, and it's telling us the same thing. But that's only true in this one specific circumstance where you choose these particular priors. It also does not carry over to like any other regression model, just OLS and a Gaussian likelihood, etc. So it's an extremely special case, but one in which Bayesian estimates and frequentist estimates coincide, even if the interpretation of them differ. Now, with MCMC and Stan and all that, then we can just sort of bypass all this. We're not going to need or be able to obtain analytic results. We can put whatever priors we want on this, and we'll get stuff. And in general, it's going to be at least somewhat different than the sampling distribution of some frequentist estimate. So does everyone understand what we've done here by basically answering the question, how can we choose priors such that our posterior distribution is the same as the frequentist sampling distribution of the OLS estimator? What I believe about the parameters is the same as what they know to be true if you were to repeat the data collection process over and over and over again and estimate OLS each time. In this one case, we can answer that question. All right. So we can, is my plot up yet? No. Why does this not work? Okay. So let us now, in the remaining time, think about a model, a generative model for the price of raw diamonds. So not the kind that you see at the jewelry store, but before they get there. Anyway, what would you say, and let's restrict ourselves to models that are linear in the parameters. So what are some things that we think are predictors that explain variation in the price of diamonds? So what might be a generative model for how the price of a wholesale diamond comes to be? We got diamond experts here?
Well, I've seen the data set in our there's carat, there's size.
These variables?
It looks familiar.
Color.
Okay. If you want to look at the available variables, you can. X, Y, and Z are like the width and the height and the depth or something like that of the. It would not surprise me if they were, but I don't know if they have blood on them, so they get sold for the same prices. Less politically. Okay, so let's give you the available variables. How would you construct a generative model for the price of diamond, wholesale diamond, from things like this? Or this might actually be, depth is some other thing that's not related to physical size. I don't know what depth is exactly. So how would we think about coming up with like the conditional expectation for the price of a diamond with all these variables except price? Robert.
You can pretend it's a linear combination of a bunch of those variables and make guesses about the coefficients.
Okay, so we're going to need priors about the coefficients eventually, but we can remember that linear models only have to be linear in their parameters. So we could include interactions, we can include polynomials, we can make transformations to either the outcome variable or the predictor variables in order to make it more sustainable that a model that is linear in its parameters, Gaussian in its error term, is more reasonable. What might we do to bring something like that about? Any economists, econ track people? Well, forget diamonds temporarily. Like, how is the price of anything usually modeled? Supply and demand. In this case, the supply of diamonds is kind of on the fixed side. So really, we're talking about variables that influence the demand for diamonds and drive up the price that way. So what is the most common thing that economists most common transformation that economists apply to prices? Log, right. And so that sort of changes it from a multiplicative data generating process for the level of the price. So if you sort of double the size, you double the price, an idea like that. If you take the logarithm of all these variables, then you correspondingly have a model that might be additive and linear in the logarithms of these things. And for a lot of things, economists tend to think that makes more sense. Okay, so let's think about a model of log price. And these predictors often also in log form. How would we, build up something like that? So what would go into mu? The conditional expectation of log price.
Are you asking us to suggest which variables should matter?
Oh, and which transformations do we want to do or what interactions? What?
Or seem like the obvious.
Right. The quality.
Seems like any of those interactions could be plausible.
Yeah. So we're probably going to have the logarithm x and y and z because these constitute the sideways height, the long ways height, and the up down. So together, these multiplied together would be like the volume of it. So the logarithm would be the sum of log x, log y, log z. Probably do something like that. But yeah, sure. And it's entirely possible that these things could, interact with anything else. So models like these, linear models, can be estimated using the rstanarm R package, which is going to, it comes with a bunch of regression sort of models. And the stand code for them is already written and already compiled. So you can just download it, call R code. It will pass your data to the stand program. It will pass what it accepts as valid prior beliefs in terms of distributions. And then it will draw from the posterior distribution of the model that you specify. Now, in the case of a linear model with multiple predictors, there's the stand LM function in rstanarm chooses a lot of prior distributions for you. It does so with a combination of maximum entropy and Jeffrey's stuff, but it forces you to specify prior mode for the R squared of your regression under a beta distribution. So implicitly, there's a beta prior on the R squared. One of the shape parameters is equal to k plus 1 over 2. The other shape parameter is free. You tell Stan what you believe to be the prior mode of the R squared. It takes that information, works out the beta distribution that corresponds to your beliefs, and then goes on to draw from the posterior distribution of everything. So that leaves us with the question, what do you believe is the prior mode for the R squared and a regression of log price on this other stuff and maybe some interactions of the variables here? Prior mode. Robert.
That'd be pretty high if these are all, especially since it's all coming from roughly the same time and place. So I don't know.
0.75. Anybody want to go high?
I think that's too low.
Too low.
No, that's too high. It's 0.5.
Too low. You think it's 0.5?
Yeah.
Totally valid. Anybody else? I mean, everybody else. You have to have beliefs about the parameters in order to obtain a posterior distribution. All right, so who thinks higher than 0.75? 2, 3. Who thinks lower than 0.5? And who thinks between 0.5 and 0.75? Okay, so I'd say between 0.5 and 0.75 is the most common one. You can certainly put in whatever you want. I put in 0.8.
Too high.
You should have told me that before I made the slides. You can run it again with 0.5. I did an interaction between caret and all the size variables. Put the factors in separate, pass diamonds. Anyway, you call stan LM much the same way you would call LM. It's just there's an additional argument, which is mandatory in this case, for specifying your beliefs about the R squared before you see the results. Now, it's important to always remember that when you do something in stan, the ultimate output is actually a matrix of draws from the posterior distribution. And you can get at that by doing as data frame, as matrix, as array, whatever you want, and just do whatever you want with the raw draws. Everything we're going to see the rest of the day, Thursday, next few weeks involving rstanarm is, you know, just sort of pre-baked functions that you can call. But you're free to do anything you want once you have these draws. So by default, it's going to give you 4,000 draws, one for every parameter that you're estimating. In this case, it has 28. And so we get draws for the intercept, draws for the coefficient on caret, etc., all the different cut variables, etc. Some of them kind of ran off the page. But anyway, you have access to all the original draws. Don't forget that. The color thing is a factor with colors D, E, F, G, and something else. Yeah. So it's going to make this into 6 dummy variables. Cut is, I think, easier. Fair, good, really good, super good, etc. So if you just type print post, where post is the object that I saved the stan LM stuff to, you get this, which looks perhaps deceptively similar to what you would get if you did frequentist output. These in the left column here are the posterior medians. On the right, we have estimates of the posterior standard deviation that are a little bit robust to weird stuff in the tails. And so if you sort of forget that you have all the original draws, you might think that these point estimates are the ultimate output, but these are just really one way of summarizing the output by saying what your posterior medians are, the medians of your belief after seeing the data. But you could also do posterior means or any other function of the 4,000 draws that you obtain. You can get a little bit more information by doing summary rather than print. So this will tell you the mean, the standard deviation, various quantiles, etc. Again, it got cut off. There's actually 28 parameters here. But if you do this yourself, you can see this output for all 28 of the parameters. So last thing that we'll go through is, okay, we've got these estimates, we've got these draws, etc. How would you characterize your beliefs about what will happen to the price of a diamond if we were to increase the number of carats by 1? So if we have, one diamond that has like 16 carats, and then we put another carat in it, and we have the same diamond, but now it has 17 carats, what would we expect to be the difference between the price of those two diamonds? How would you ascertain that?
Like the average coefficient.
The 7.4?
This is the median. I think it should be
Mean, median, etc. Okay. But this is how much we expect, or the median of our beliefs for in terms of log price. What would be our posterior distribution about the expected difference, or the difference in price in regular dollars rather than log dollars? What now? So you just EXP 7.4? Yeah. Inverse? Inverse what? Inverse log? That's EXP. Marlon?
plus 7.4.
No. Okay, we're running out of time, so I'll just tell you the answer. The answer is you don't figure it out from this. You figure it out by going back to your generative model and working out the scenario that you're interested in. So you call posterior predict, give it the object that we created, say we want 500 draws, from the posterior prediction of log price given the predictors as they are. Then you make yourself a new data set, making sure you have the same observations as more. You add 1 caret to all of those diamonds. You call posterior predict again with new data is this to get what you predict log price to be if every diamond had 1 more carat in it. Then that's predictions in terms of log price. We don't care about that. So we do E of this minus E of that. We can divide by 1,000 if we want to put this in terms of thousands of dollars rather than cents, whatever. We can make a histogram. We can plot the density. We can do summaries of this to get the expectation and the mean, median and the interquartile range and anything we want of EXP of the predictions in one scenario, EXP of the predictions in the other. That tells us the distribution of beliefs if we were to change the carats by 1. And so for models like this, and models we'll talk about on Thursday, where you have like complicated transformations and all this, the answer is never to just look at some very brief summary. The answer is to come up with endogenous unknowns that, given your posterior beliefs about the betas and the alpha and sigma and all that, imply you predictions about these things, and then do interesting stuff directly on predictions of price. And so here we see the density of that. It's generally going to be around 30 or so, but it has an extremely large tail. And so that is what, given the data in our starting prior beliefs, we believe to be the distribution of differences if we on dollar price if we were to increase the number of carats by 1. And so basically the answer is plot it, or at least generate the thing. You can make a plot if you want. You can do numerical summaries if you want, but don't just take something from a table like this, because it implies the answer that you're looking for, but often in a weird nonlinear way that's not evident from 7.4. 7.4 is not a complete characterization of your beliefs about the carat thing. And so in order to characterize that completely, make the predictions, make the plot. All right. That's it for today. Andres?
Should you be worried about such a long tail?
That's what you believe. So basically you can't rule out that there's some like very high quality diamond somewhere in the world that's, base price is, very high. And so if you added 1 more carat to it, it would become like the most valuable diamond ever. It's not inconceivable under your model. But basically you're saying that almost all of them are like less than 40,000.
I don't know. How long should it take to process data set?
It's a pretty big data set, so it may be a few minutes.
Kind of taking it all.
Oh, your computer's about to explode? Just wait a little while longer.
So if you had a model like this,